There we go. So chapter 6.7, there's basically 4 types of problems that you do in this section, and I want to go over each type. The first type of problem is solving for a variable. So let's say we have something like this. And you're asked to solve for F2. The trick for these, oh, forgot the R. The trick for these is you want to get rid of the denominators. So the way we can get rid of the denominator in this problem, multiply both sides by F1 plus F2. So if we do that, we'll cancel the denominator on this side. Of course, what we do to one side, we have to do to the other. So what that'll give us is something like this. Now, what they like us to do in this section is whatever answer we get at the end, we can very easily get an answer different from what they have in the text, but it's still the right answer. And what they're going to want us to do is whatever answer we get, we want to merge it into one term if we can. So I'm going to do this in a way that, say, doesn't lead to a single term to begin with. So I want to isolate, well, first off, we're solving for F2. So this might actually turn out to be an easy one-term type problem. But let's distribute F. Let's get rid of all the barriers, like we got rid of denominators. Let's get rid of parentheses. So we've got this. Now we're searching for F2, and we've got F2 in 2 places. One thing we can do is we can factor F2 out. If the F2 is in 2 or more terms, and those terms are on the same side. So we need to move this one to that side, and then we can factor out F2. So now we can factor out that F2. So now what we want to do, we want to get F2 by itself. So we're going to divide this entire piece on both sides. Now, we can't turn this into a number, so we're just going to leave it as F1 divided by F1 minus F. I'm just going to leave it that way. And that is going to be our answer. Now, what can sometimes happen with these, again, I'll just mention it. You can get a situation where you get an answer with two terms. I'll show you a situation here where that turns out. And you need to merge the two terms. So, for example, let's say we have this. And let's say we want to solve for the lowercase r. Well, again, we want to get rid of denominators. So we can multiply both sides by r plus r. You could also cross multiply with I times r plus r, and then 1, there's an invisible 1 underneath the I, times e. Let's say we multiply both sides by r plus r. Now, at this point, I might say, since we're trying to isolate this and sort of dig it out, let's divide by r, or I rather. So that takes away the need for the parentheses. And then subtract capital R. So far, so good. This is a correct answer. This is perfectly fine. But if you were to look in the text, excuse me, they actually want a different answer. They want it merged into one term. So the way you could do this, we need a common denominator. Again, there's that invisible 1 there. I'll make it become visible. So let's multiply top and bottom by capital I. Now combining like terms, or now they have a common denominator is what I mean, not like terms. That's a different sort of thing. That's going to be our answer. In the text, at least, this is the answer they're looking for. They want you to merge the two terms into one term. So that's one type of problem you'll see in 6.7. Now, the other types of problems are story problems. And let's take a look at this one. A company is planning to manufacture small canoes. There's a fixed cost $20,000. This is a monthly fixed cost. And then there's a $20 cost per canoe. So the first thing they want us to do is write the cost function C, producing X canoes. Excuse me. Well, a cost function is this. We defined it as C as X is fixed cost plus variable cost. Now, what's the difference? Well, fixed costs are things that you're going to have to pay even if you don't make anything. So if you have a factory, you have to pay rent. You have to usually pay some kind of insurance. You might have to pay some low-level electricity bill just to keep certain things going, like maybe an alarm system, something so smoke detector works. Let's see, what else might be fixed costs? Rent, insurance, taxes, property taxes, things like that. Variable costs, these occur usually when you start producing things. These are wages. This is the extra electricity you'll need to produce something. Excuse me. This could be parts and materials. And in the variable costs, these are usually hidden in the cost per object. So how much does it cost to make this object, excluding the fixed costs? And that's what this tends to be right here. So to find the variable cost, it'll be the cost per object times the number of objects. I'm using objects. It could be widgets. There's different terms for this. Now, the cost per object is usually represented by a lowercase c, and we multiply the number of objects we represent as x. So what happens is that the cost function for the variable cost, we represent it as cx, where c is the cost per object and x is the number of objects. So for our cost function, it'll be cx, the fixed cost, which is 20,000, plus, now c is going to be 20, and then the number of objects, x. So for each month, we have $20,000 of fixed costs that we have to pay for no matter what. Rent, insurance, taxes, maybe little low levels of electricity. And then we have the costs when we're actually up and running. Wages, the extra electricity, repairs as machines are running, materials for whatever we're producing. Now those turn out to be about $20 per canoe in this case, or $20 per object. And then the number of objects we have, that'll give us the entire variable cost for the month. Excuse me. So that's how we would answer part A. Now part B, I'm pretty sure it's going to be average cost, yes. Pardon me, it's itch in my throat here. I drank some water. I think it just went down the wrong tube. I'm not sure if this is going to help, but all right. So find the average cost. Now, average cost, this is total cost per object. So what we do is we take the total cost and we divide by the number of objects. So we take our total cost, which is 20,000. And then the total number of objects, which is x. And that's going to be our average cost. And your total cost number of objects. And that will give you the cost per object on average. Now, here comes the question. How many canoes must be produced each month for the company to have an average cost of $40 per canoe? right. So what this means is this. You take this average cost function, which is just the total cost function totally divided by x. And we let this be 40. And we multiply by x. And that's going to cancel the x here. We're going to solve for x is what we're going to try to do. And so by solving for x, we can multiply both sides by x. Again, we want to get rid of the denominator. So let me start that over again. So what we want to do is we want to find how many canoes for this kind of thing to happen. So to do that, we got to solve for x. And again, no denominators if we can help it. And so we can do that by canceling this denominator. That's why I multiply by x. So that'll go away. 40x is 20,000 plus 20x. Subtract 20x. We'll get 20x equals 20,000. Divide by 20. Excuse me. And so we're going to get x is equal to 1,000. And that's going to be our answer. All right. So that's one kind of story problem that comes up. There's another one. Let's see. All right. So this is called a motion problem. And there's different types of motion problems. The idea is this. So when we talk about motion, we take miles per hour, and that's literally miles divided by hours. So if you drive 55 miles per hour, well, that means you're doing 55 miles in 1 hour. Now, this is called a rate. So the way we write this up abstractly is we say this is rate equals distance over time. Or put another way, R is D over T. So this is an important relationship to have. And depending on what the problem is asking for, you're going to rearrange this in different ways. The one that they have in the textbook, that version, the way they got it, if rate is distance over time, let's multiply both sides by time. Well, that means time will cancel. So, excuse me. TR equals D. This is also a good relationship to have. If you need to solve, maybe here we solve for D, but you could solve for R or solve for T as you need to. So for example, we could solve for R or solve for T. So for R, excuse me, divide both sides by t, and we get our old rate equation. R equals d over t. Excuse me. Or we have tr equals d. We're solving for t, so we divide by r. And this is the one they have in the textbook. And this is one you use a lot in these problems. Time is distance over rate. So each of these three equations, these three equations, this is the one that we started with, and then we got this, and then we sort of circled around. But each of these can be helpful for these problems. So let me do an example. So let's say we have this. A car travels 300 miles in the same amount of time a bus travels 180 miles. So in some amount of time, let's say it was, I don't know, 3 hours. Well, no, not 3 hours. Oof, you'd be driving pretty fast. Say 6 hours. So say in 6 hours, the car travels 300 miles, the bus travels 180. Just to illustrate. I don't know if it's actually 6 hours. I'm just making that up. The point is, in some fixed amount of time, the car that's driving faster will go farther than the bus that's going slower. Excuse me. Now, the rate of the bus is 20 miles per hour slower So find the rate for each vehicle. So the only thing we actually know about these rates is the bus is 20 miles per hour slower. Now the thing to keep in mind here is that's what I was going to say. We are looking for rates. Now the rates, they'll sometimes call them in the text average rates. It means the same thing. Pretty much all the rates are going to be dealing with are average, really until you get to calculus. And in calculus, we learn about how to find instantaneous rates. But in this case, we're dealing with average rates. Rate, average rate, for us will be the same thing. So let's break this down. And we're going to break it down using the same technique we had solved story problems in the past. I'm going to do the 4 steps. I'll leave the 5th one off just for time. The 5th one is where we sort of check it. Does it make sense? Is this a logical kind of answer we would expect? Like, we should expect the car to be faster than the bus. So the car's rate should be more than the bus's rate. If that's not the case, we might have done something wrong. So we want to keep that in mind. But I'm just going to do the first 4 just for the sake of time. So first off, what do we know? Well, the car went 300 miles. And the bus, let me double check this, it was 180 miles. And they did this in the same amount of time. So whatever this amount of time is, we know they did this in the same amount of time. And then we also know the bus is 20 miles per hour slower. We do know that. So what about unknown? Well, there's a number of things we don't know. For one, we don't know what this amount of time is. We also don't know the rate for the bus. We also don't know, oh, this is looking kind of dire, the rate for the car. Now, usually when we do these problems, there's only one thing we don't know. There's a bunch of stuff we don't know. But I'm going to make an argument here. We're better off than it looks. We know something about the bus. It's 20 miles per hour slower than the car. So if we know the rate for the car, we all of a sudden know the rate for the bus. Subtract 20 from the rate of the car, we've got the rate of the bus. So this one, we kind of know something about it. If we know this, then we'll get this. What about the amount of time? So what we actually do know about this, I'll slip in a little asterisk. We know it's 20 mph less than the car, which is what we've got here. And there's also a little asterisk, and I'll have to insert this in here. Well, for the time is distance divided by rate. Take the car. We know the car went 300 miles. If we know the rate of the car, then automatically we'll know how much time. We just take the 300 miles, divide by the rate of the car, that would give us the time. So here's the thing that we're running into. If we know the rate of the car, which we have no idea about whatsoever, then we'll know the rate for the bus, and then we'll also know the rate, the time. We'll know the time. So the key thing that's missing that lets us know the rate for the bus and the amount of time is that rate for the car. So that's going to be the unknown we choose. So we're going to come up with our equation. Let x equal the rate of the car. Now, a key thing to remember is these vehicles do this journey in the same amount of time. So time is distance over rate. So for the car, it traveled a distance of 300 miles, and unfortunately, we don't know the rate. We called it x. So it's an unknown rate, x. Now, in the same amount of time, so I'm using the same t here, the bus went 180 miles, and then what's the rate of the bus? Well, we really don't know, but we do know this. It's 20 miles slower than the car. So we take the rate of the car, subtract 20 miles per hour off that rate. That gives us the rate of the bus. Now, again, this is the same amount of time. So that means these are equal to the same time t. And if this equals this, and then this equals that, then these two expressions are equal. So this is the equation we're going to solve. So what we can do, there's a couple ways you can solve this. You could solve it using cross multiplication, or you can use the factor method. I'm just going to stick to the factor method because we've been doing it so much. It's just something to keep practice. So list the denominators. Factor the denominators. Well, nothing's going to happen here. X is its own factor. X minus 20, there's nothing to factor out. So it's going to be its own factor. And then let's make these factorizations the same. So this one's missing an x minus 20. This one's missing an x. So now the factorizations are the same. What this means is we'll multiply this through, and that's going to let us cancel these denominators. Again, that's always our goal to start. So we'll do some canceling. Again, we multiply both sides by the same amount. So here the x's, those are going to cancel. And then here the x minus 20 is going to cancel. The end result is we're going to get the same thing if we would have cross-multiplied, but just sticking with that consistent technique. So you have x minus 20 times 300 will equal 180 times x. We'll need to distribute the 300. $300x minus 6,000 equals 180x. Subtract 180x from both sides. And so we'll get 120. And let's see, we'll get 120x equals 6,000. And we'll get x is equal to 50 miles per hour. And remember what x is. X is the rate for the car. Now, we still need the rate for the bus. The bus is 20 miles per hour slower. So x minus 20 will be 50 minus 20, or 30 miles per hour. And that's going to be our answer. So that's the motion problem. So we have the formulas, we have the motion problem, we have the cost problem. The last kind of problem we run into is work. So let's see. So let's say we have this. You're working with your cousin. I'll call this work. You're working with your cousin, and you can finish a table in 3 hours. So say you so working with your cousin, you plus cousin. You can do this in 3 hours. Your cousin can complete the job alone in 4 hours. So you're just building a table is what you're doing. Or refinish a table. You're refinishing a table. How long would it take you to refinish the table? So let's take a look at this. So the way work problems work is if you're looking at the ratio of one job over time. So let's give an example. Let's say one job takes 10 hours. Yikes. So what that means is we're going to deal with one job per 10 hours. So let's take a look at this. Let's say you worked at this for 20 hours. In 20 hours, how much could you accomplish? Well, if we take one job per 10 hours and we multiply by 20 hours, what we'll get is 20 over 10. Because again, you're going to treat this like fraction multiplication. You have the visible 1 here. We're going to multiply across to get 20, multiply across to get 10, and what you'll get is 2. So the way this works, when we take the amount of time and we multiply by this rate, it tells us how many jobs can we do. So if we do one job in 10 hours and we have 20 hours, we can do 2 jobs. Likewise for 30 hours. Again, we'll take the rate, multiply by the time. We'll get 30 over 10 or 3 jobs. So if we have 30 hours available to work, we can get 3 jobs done. Now, let's say we have 5 hours to work. We only have 5 hours. We'll have 5 over 10. That reduces to half a job. So the idea with work is this. You have job over the time it takes to complete one job. And then you take this very particular rate, multiply it by the amount of time you have available to work, and that will tell you how much of the job you'll get done. If you have more than the time it takes, you'll get more of the job, maybe 2 jobs or 3 jobs done. If you have less than the time it takes, you only get a fraction of the job done. So let's take a look at this again. Let me rewrite this. So it's a little more story problem-like. So you and your cousin let's see, what was that? A table in 3 hours. And alone, your cousin can do it, refinish a table in 4 hours. So how long is it going to take you to refinish a table? So that's what we're looking at. So in this case, what we want to do, let's do our breakdown. So what do we know? Now the book gives a certain technique for doing this, and this will come up, looks like it's going to be the third step. We're going to use a chart. But what do we know? You and cousin? Well, it takes you 3 hours to refinish this table. Your cousin, working alone, can do this in 4 hours. And let's see, when we go back here. So that's basically what we know. What is unknown is time you need to refinish a table. So that's what we're missing. So let's start breaking this down, and we're going to use this job to time ratio. So we're missing the time for you. So that X equals your time for one table. So if we take a look at job to time ratios, for your cousin, well, they can refinish one table in 4 hours. So that's one job in 4 hours. For you with your cousin, you can get one job or one table in 3 hours. Now what about you? Well, you can get one table or one job, and we're not sure what the time was, so we just called it X. You have one job over X hours. All right, now we should have enough material here to come up with the what we're going to need to come up with an equation. Let's see. So the way we're going to come up with this, when you work, we're going to look at the fact that you're working on a project, say, with your cousin. So if you're working together, you're each going to contribute part. So your part plus the cousin's part gives us the total. So what we know is this. Your part is one job in X hours. Unfortunately, we don't know the exact hours, but we're going to try to discover that. Your cousin has the capacity of one job out of 4 hours. So whatever you accomplish and whatever your cousin accomplishes, that's going to give you one job done in 3 hours. So this is what we're going to solve. Let me just double check something here real quick. So we want to solve for x. So again, what we want to do, we want to get rid of the denominators. We have a denominator of x, denominator of 4, denominator of 3. So we can list our denominators. X is just x. 3 is just 3. 4 is 2 times 2. We want to make these factorizations the same. So this, we need a times x here. This one needs a times 3. Let's see, this one needs a times 3 and a times x. And this needs a times 2 times 2. This is a times 2 times 2. So what we're going to get is 12x, 12x, 12x. All right. So this is what we're going to multiply this by all the way through. So we're going to multiply both sides by 12x. Now, if we distribute here, we'll get 12x times 1 over x plus 12x times 1 over 4 equals 1/3 times 12x. Now, looking at cancellations, the x's here are going to cancel out. Now, 4 goes in the 12x 3x times. 3 goes in the 12x 4x times. So now we don't have those denominators. So you get 12 times 1 plus 3x times 1 equals 1 times 4x. And then 12 plus 3x equals 4x. Subtract 3x from both sides. We're going to get 12 equals x. That is the correct answer. So it turns out, if your cousin can do this table by themselves in 4 hours, and the two of you working together can get it finished in 3 hours, well, how much help are you contributing here? Well, apparently it would take you 12 hours to do it by yourself. So something to kind of keep in mind. Now, when you work together with someone, there's all kinds of other variables involved, so it might not be quite this dramatic. But you can put it like this. If it takes you 12 hours to do something, and it takes somebody else 3 hours to do the same thing, to this, working together, you could get it done in 4 hours. So now, I don't think it's quite that simple, but that's sort of what turns out. Now, there is a way of doing this with a chart, but I use sort of the parts approach, where you have your contribution, there's your cousin's contribution, and those contributions together are going to give you the total finished project, or the finished rate for that project. So that's what we've got. And let's see, it's 206. So that's 6.7. Those are the problems I wanted to cover from that section. What I can do the next few sections are similar, these early sections of chapter 7. So I'll stop here for now. What we can do is we'll take a look at chapter 7. I'll do some overview sections for chapter 7 tomorrow or on Thursday. And I can do some other overview sections also if we're kind of coming down to the semester. But I do have full-blown lectures I'm putting together, so they're just a little more detail, a little more time put into these topics. So I think I'm going to stop here. I don't think there's a real good way to do chapter 7.1 very quickly. There really isn't, not in, what would it be, 8 minutes. So I'm going to leave it here for now. If you have any questions about these, let me know. And other than that, have a wonderful day.
Thank you, Joey. Have a good day.
You too, Priscilla.